Matheus Curado Ferreira, who's going to be talking about Cosmological, Ghost Collider, and Bootstrap.
Okay. First, thank you to the organizers for this event. Thank you everyone that is here. I'm a PhD, okay, at CBPF, Brazilian Center of Physics Research. It stays in Rio de Janeiro. And I will talk about this proposal that I have for the Cosmological Bootstrap program. Okay. This was supposed to work. Okay. Yeah. So the goal, first, when you do this collider, cosmological bootstrap, what is the goal? Is to set the initial conditions of the universe. When what I meant by that is the correlation functions at the end, for example, at the end of inflation. If you take inflation as your primordial theory or the theory that describes the primordial universe, okay? So these structures will influence, of course, in the large-scale structures of the universe. So they are very important, okay? This is not a new idea, this idea of collider thing. This is not new. This goes back to Zeldovich, a Russian physicist, brilliant physicist. However, in my opinion, okay, my personal opinion, this was very well established in 2015 by Maldacena and Haqqani Ahmed when they published this paper, Cosmological Collider Physics, that basically can be summarized in computing signals like this configuration. I will talk more about that. Let me just give you some, okay. In cosmic inflation, you can have some non-Gaussian signal, okay? However, due to the slow hole phase, the slow hole regime of the theory, slow hole parameters, you will see that if you compute this guy here, it's almost zeros. You know, that doesn't contribute much. And even if you consider another massive field, I will explain better why you consider this guy. This also is very suppressed. However, this signal, no, this signal is a good signal. So the idea, basically, roughly speaking, the cosmological collider, it's that we have this massive, very heavy field in the bulk or in the very past, you know, and he somehow interact with the inflatons and leave this signal in the bispectrum configuration of the inflatons, in the shape function, okay? And so that is the story. You have a cosmological theory, okay? You have trilinear interaction. You can have another extra field that will not live at superhorizon scales, only in the bulk, and you can do somehow particle phenomenology with this idea that everything can decay into inflatons, basically. So how it's done, okay? There are several ways that you can do. I will talk about the way that I'm doing. You can, in this bootstrap way of thinking, you define your integral or some seed, we call seed function. You have some interaction, you have some symmetries, and you skip all of the difficult things, looking at the amplitude, looking at the symmetries that you can have, that you cannot have, and build up your correlation function, okay? Everything that we do in cosmology, why the diagrams are so like this, you know, some people here, we saw a little about in correlation functions today. So this is an in diagram. So why in? So in cosmology, we look up to the sky and make observations. We don't do experiments. So what we see spatial correlations. So we need to integrate at fixed time. So that is why we use this formalism. Okay, this is if you want a physical reason, now you have it. So here you have a boundary, something like you can think about your conformal time going to 0 here, and here minus infinity. So if you have an extra field, you can think as a heavy curvaton if you are a cosmologist, okay? You can imagine that he can interact with the inflaton at this level. So you will have a 4-point function, okay, with an exchange of a scalar particle, a heavy particle. So this is the seed that I'm calling the seed function. This is a structure that you can factorize from the 4-point function. So now you can think like, oh, okay, but this guy is taking Feynman integral, so what is the bootstrap thing here? So from this simple interaction, for one single interaction, you can build every interaction that you want. So that is the bootstrap way of thinking in this program. So you can even do a construction only from boundary things. There's more asymmetric approach. You have these approaches, but you also have this that you do a little of bulk reconstruction and make everything from that. So, okay, so this is the seed function. And we don't know how to do these integrals because these propagators are proportional to products of Hankel functions. This is very hard to do. Okay, so what do? We translate this to a differential equation. And this differential equation basically gives us every information about the symmetries that we have. So, for example, in the standard Bootstrap program, that I'm going to give you a sketch here. I will talk about my ghosts just a moment. You have two boundary conditions that you need to handle with it. The factorization limit that I call this one, your propagator needs to be regular there. And also this folded limit for you to have a Bunch-Davis amplitude, okay, consistent, regular. You need to subtract for example, these singularities that appear in the solutions. You can see that by looking at the differential equations. Okay, so this is the story.
Sorry, could you comment on what's U and B in? What are these variables that you're using?
Okay. I think I defined them here. They are like Maldusson variables. I call them kinematical variables. They are just, okay. So they are representing the momentas of the field, okay? So you have this S, like you can call S channel if you want. So you have key, R, and so on. So you relabel them like these things, okay? And they simplify things. So you can write this differential equation and work on this assumption. Of course, that there are some symmetries about the kinematic of these variables also. Yeah, but I will not get into that. I will just comment in the end. But they are just like more distant variables.
I'm sorry, a follow-up question. And the equation of motion is just in U, right?
U?
In a variable U, I mean.
Yeah.
Or
yeah.
it doesn't involve V derivatives?
Yeah.
Okay.
You will have the same thing holding for V as well. There's this constraint equation that I will tell you about in the end. That also it tells you about the conformal symmetry. I will get there, but yes. Okay, so you have the solutions you solve. It's not hard if you know how to solve it. These guys have shown, like Nima, Baumann, and Pimentel, they will be here next week. I think it's a good opportunity to learn about this. This is just the homogeneous solution Mathematica can give you. And this is some difficult part, but with a Taylor ansatz, you can solve it also. And finally, okay, getting back to the Bootstrap thing, there are ways to map these things to the quantities that you can observe, like the bispectrum or the shape function, or even corrections, leading order corrections, next leading order corrections to the power spectrum due to the presence of this very massive field, extra field, okay? There's this way you can do using the general seed function that I put there in the beginning, or you can use weight shifting operators, okay? There are different, you can get different things by using these things. Weight shifting, you can really capture the perturbative results from inflation, like single field 2002, that Maldacena has done it, the Caminelli model for inflation, higher derivatives, so on. And here, you cannot, using this general seed, you do not get exactly the perturbative expansion. However, you get something very analytical that also reproduces in a plot, you know. So anyway, two things that you can do.
Sorry, in the previous slide, this epsilon.
This one?
No. Next one. So you're defining this zeta phi over square root of 2 epsilon.
Yeah.
Lag. So what is this?
So, okay, yeah. This is the, well, this is the scalar curvature, degree of freedom, when you do cosmological perturbation theory. The whole thing about the Bootstrap, I'm speaking a little fast. You can do things like in an effective theory way of thinking. You can build something in the sitter, okay? Then you can deform the solutions to get the inflationary amplitude. Inflation is not the sitter, so. And the way that you map your solution to inflation, of course, is by changing the variables, okay? There is a relation in a flat gauge in perturbation theory in cosmology. When you map this, there will be your scalar matter, your scalar field to the curvature scalar degree of freedom. This is the slow hole parameter. So your bispectrum will be given by this guy. So you can rewrite this guy in this way to plot the shape function. That is actually what you can do phenomenology. You do phenomenology with this object. Okay. So these are just the Hubble constant. This is the momentas. Also, one technical thing, that 4-point function that I put in the previous slides, you can always take these limits. The Maldacena has, we learned from him how to map this 4-point function to 3-point function by taking soft limits. So you take one lag, and you take a soft limit of this guy, and you evaluate this lag on the background, and it's analogous of doing all these transformations. Okay. Anyway, so this is the standard procedure, very summarized. Try to give you very sketch. Pimentel will be here, so he can tell you more about it. And now I will talk about my proposal. Okay. Here at the IFT, during perturbative quantum gravity school, I learned about these ghosts. So I find out this ghost inflation work from Arcani-Ahmed, Creminelli, Zaldarriaga, and I start to give some approach to approach this ghost inflation, ghost things with this cosmological bootstrap ideas, cosmological collider ideas. So first thing that I notice, it's good to know about these guys, is the ghost inflation is ruled out by Planck because of the spectral index is exactly 1. We hope that this should not be exactly 1 in a real cosmological model. So these guys as ghosts, as inflatons, sorry, they do not make much sense anymore. However, we could think about these quasi-single field theories or multi-field theories or cosmological collider about something that there is exchange in the bulk. So I have the idea of thinking about these ghosts as massive objects living in the bulk. So previously, they didn't have mass. So I need to add this mass. So it's possible you can do cosmological perturbation, define the quadratic Lagrangian with some mass, given some conditions, of course, but you can do it. And okay, and I built this scenario of ghost collider, okay? So the funny thing about the ghosts is that they violate Lorentz symmetry. And why they are called ghosts, this is always polemic for me, so always troubling, but the original model from, I didn't put the Lagrangian here, it's very big. The original model from Creminelli and Arcani-Ahmed, they consider a chi-essence theory where you have instabilities that could lead you to this famous ostroglastic problem. You know, you cannot well define the fundamental states for these scalar guys, so people call them ghosts. However, these guys find a way to stabilize the whole thing. So why am I calling ghosts? So we should ask them.
Sorry, what is it that they are stabilizing?
Well, I didn't put the Lagrangian here about the 2004, this work, but the point is, when you take this Chi's essence term in the Lagrangian, and you calculate the background equations of motion, you see that to have an asymptotic limit, well-defined asymptotic limit, you have two choices. So these two choices that you have to impose, something like the derivative of the background field equals to 0, something like that. The both choices leads to these instabilities. However, one of these choices, if you add higher derivative terms, it can make stable the whole theory. And Nima did that. However, he truncate the whole thing, arguing that you can build a low energy effective action for these ghosts, and there is something about it's not so hard to see. You see that the other operators that he didn't put there, they are very irrelevant, okay? So the price that you pay is that you have this kinetic ugly term here. This is not usual, okay? So this leads you to this thing. So somehow you can stabilize the guys, but you lost some Lorentz symmetry. But the ugly thing about this is that they are still scale invariant. So anyway, we add this mass to these guys, put them in the bulk, okay, and try to make some, plotting these things, looking at the shape function of these structures. We are finishing these things. I just bring something here to see that, for example, if you take lower masses, it's more probable that you see higher oscillations, okay? And there is another interesting thing is that the shape function of this ghost in a bulk can be in phase with the same structure when you consider only de Sitter things. Massive de Sitter that do not violate Lorentz symmetry, for example. Anyway, these are interesting things. We are still working on it, okay?
Sorry.
Okay.
Maybe you can say a bit more about this graphics. What is it exactly that you're plotting? This I
okay.
is
this is the seed
amplitude
function
that you are trying to...
Yeah. Okay, this is the seed function, okay, over one of the cross ratios, okay? And here also, so, but this guy, I'm comparing the de Sitter case, the standard case of de Sitter that Nima has done it in 2019, with the one that I found it, okay? I'm just trying to show here, but it's a little ugly, but we can put them in phase, okay? But there is a magnitude difference on the signal, okay? And here's just ghosts. However, you can see that if they are more massive, they will oscillate in different frequencies. So, just that. Okay. So now the bootstrap thing. So I can plot things in the squeeze limit, even do phenomenology. However, another totally thing is derive the full shape of the solutions. This is very hard. This is where the bootstrap thing gets into this talk when you want the full solution. And the problem is that the bootstrap equation with these ghosts in the bulk is very ugly, as you can see. There are some details here. This L means for the type of particle that you put in the bulk. So if they are conformally coupled particles, this will be -2. If they are massless particles, they will be 0. Okay? And this is very hard to solve. I went to Italy a couple weeks ago with Pimentel. He's helping. We are studying these things. And the interesting thing about this is that the singularities that we have before seems to disappear. So somehow we mix the symmetries and we lost some singularities. Like the folded limited is not obvious. We didn't find it. And even the factorization limit. So I put here just for curiosity the case of pure ghosts, okay, when you only have ghosts, because, for example, I'm almost finishing, okay? The problem of the flat space limit, we didn't find this for example, this factorization regularity in the equations. However, there is this strange, very strange thing I saw in Italy. We don't know, we are still trying to understand. When you consider only ghosts, you don't have a very well-defined flat space limit. You don't have it. You can see here, you have things like, if you take this minus infinity with respect the argument of the Hankel function of, or if you want, with respect eta, and k, you will have some structure like that. While in the sitter you have something like this. So you see by this guy that this is not exactly flat space. You will not have a flat space. However, the singularities, somehow they are there for the case of pure ghosts. We don't know how, but they are there, and the whole thing have the conformal symmetry. That is very, very odd since we are breaking Lorentz in the bulk, okay? This is strange, we are still trying to understand. And another thing, I will say it, just a provocation here, is this equation is called conformal constraint equation. It tells you in this cosmological bootstrap framework that the interactions that will appear in the theory somehow are controlled by conformal symmetry. Okay, so for example, if you take the de Sitter case, there is this one. This operator is like the differential equation for the de Sitter, the bootstrap equation for the de Sitter. I showed in very previous slides. So if you take this kind of source term, it will be annihilate here. So this is a good source term that will represent an interaction for conformally coupled fields in the theory. And that is the strange thing, because when we compute these guys that break Lorentz, they still satisfy the same constraint equations. So the conformal symmetry is there fixing things, but we still don't know how to really solve it. So these are the topics that I'm also thinking about. And that's it, okay? This is some references. There are a lot of references. And thank you.
Questions? While people think questions, I can ask you something.
Okay.
No.
Thank you very much for the talk. I also happened to be at the same conference you mentioned last year. And what I remember is that a lot of this interest in higher derivatives and ghosts and etc. is usually due to, perhaps not usually, but one of the good things it does is that it can give you a renormalizable quantum theory of gravity.
Okay.
So what I was wondering is whether this approach has any good properties regarding that, whether it is interesting along those sides, or if not, what is your interest in this particular model?
You know, my interest in this particular model is because we are breaking symmetries. So I really want to do some, or have some phenomenological signal that is different from the standard one, that, you know, shows some symmetry breaking thing, effect at least. So that is my goal. Now, the action itself, you know, if you look at this low energy effective action, it's not renormalizable. So, and this discussion about renormalizability, we don't have the discussion like the people of quantum gravity have here. It's different, you know. We already have the analytic solutions of the correlators because of these differential equation approaches. So we skip that part.
I see. Thank you very much.
Thank you.
Questions? Okay, so I have one question. So in what you are doing, you're not considering the pure de Sitter case. So can you study this ghost-like thing with the mass term that you're having in pure de Sitter and try to see whether it makes sense there as you have more symmetries and you understand more like the structure of the theories that you can have there?
Yeah, the thing is, this ghost, even massless, you can put him in the sitter, background. Choose the conformal factor being 1 over eta, whatever. But the guy itself breaks Lorentz symmetry. So it's an observable that breaks this symmetry. So I don't know if I can construct, I don't know if I have a way to construct him being a de Sitter invariant completely.
Okay, and one last question. So this is kind of an effective field theory approach.
Yeah.
Do you have some vision of how, in a more complete theory of even quantum field theory on this kind of space-times, will this thing come to be, or how is this a natural expectation to have in an inflationary scenario? Or
Yeah.
it's just something that we are playing with because we can?
Yeah. The idea, as I said, the motivation, the first motivation was phenomenology. So this program, sometimes it's hard to find something new to do, okay? And me and my advisor, we want to explore these scenarios where you break symmetries. Like, for example, Pimentel has one proposal called boostless. And this goals somehow appeared as, we can really see and try to construct a signal, look for this signal, and this signal should have some new effect because it's not a standard de Sitter signal. Now, about a fully theory, the problem is you have very higher order derivative terms. They are irrelevant in some sense, but I don't know if we can really construct an analytical thing considering all these guys. That is the problem. For this lower effective approach, the modes are analytical. So this is a good input to the program. If we don't have, I don't think we can do cosmological bootstrap with non-analytical mode functions. At least I don't know yet. So.
Okay, so let's thank the speaker once again.
Thank you.